Hello all. Today it was the last talk of the day, and I think it's good because we have a little technical hardcore talk, as I think it's more light talk and about some vulnerabilities in industrial DTM components and how one vulnerable DTM components could be a key to the full ICS kingdom. My name is Alexander Bolshev. I work as ICS Informational Security Auditor at Digital Security. I hold PhD and also work as assistant professor at St. Petersburg Electrotechnical University. My main research area is distributed system security, and I'm yet another man wearing some color hat. Here is my colleague.
Yeah, my name is Gleb Cherbov, and I'm also information security auditor and researcher at Digital Security. And my weekdays is the penetration testing and some kinds of security assessments. And from time to time, I hack some hardware. I like it.
And here is the agenda for our talk. At first, we will give you a small ICS 101 introduction and list some key features of FDT DTM technology. Then we will talk about our research scope and fuzzing technologies. After that, we will present short vulnerability statistics, and at the end of the talk, we'll look in details in some vulnerabilities, discuss FDT version 2 standard problems, and make a small conclusion. So in next few slides, we will review the key points of FDT DTM technology. Time for some theory. ICS, you may know, stands for Industrial Control System. Today, ICS infrastructure are commonly used in every factory and even in your house too. ICS usually collects data from remote station, also called field devices, transmitters, or remote transmission units or tools, processes it, and uses automated algorithms or operator-driven supervisory to create commands to be sent back to the field devices. You can find thousands of devices in a facility. To control them, plant asset management, PAS or AMS systems were invented. PAS systems are tools for managing plant assets, field devices, controllers, gateways, and other things. They lie on the upper medium level of plant ICS network and are used for controlling, monitoring, configuring field devices. Different field protocols flow in the industrial buses where field devices exist. Here are some of them: HART based on 420 mA current loop, Profibus DP and Modbus, which use RS485 digital line as a physical layer, Manchester bus powered protocols such as Profibus PA and Foundation field bus H1. And you can see several field devices on this slide. They are designed to measure temperature, pressure, and other parameters. We review a fuzz DTM components for all of these transmitters that's shown on the screen during our research, and why the industry need the special technology for them. Imagine a modern industrial facility, power plant for example, and think about how many different field devices exist in its infrastructure. Tons of temperature sensors, pressure sensors, and other useful transmitters. These devices are from different vendors, work with different low-level protocols, and organized into complex hierarchical networks. Now ask yourself how to support all those devices. Even working to each of them with a handheld communicator could be painful. Another problem is a usage of DCS. When you're creating a DCS, distributed control system, or SCADA, you need to work with all these transmitters. So we need the industry needed that technology that unite all the transmitters, and the solution exists, and it's called Field Device Type Manager specification, invented by FDT Group. In short, FDT standardizes the communication and configuration interface between all field devices and host systems, and DTM provides a unified structure for accessing device parameters, configuring and operating the devices, and diagnosing problems. According to FDT Group, the creator and maintainer of FDT specification, FDT covers almost all levels of the plant, from the field devices, from the field level, from the sensor and actor bus, up to the enterprise resource planning systems on the upper levels of the ICS infrastructure. And on the slides you can see exact places in the ICS infrastructure where DTM components or FDT containers exist. It's OPC, OLEV for process control, plant asset management IMS or PAS, distributed control systems, human-machine interface, and manufacturing execution system MES. The key DTM component concepts according to FDT group are shown on the slide. This is a long list. I'm sorry for showing it, but I selected with bold the key concepts that could be a nice point for attack. For example, automatic generation of dependent parameters, diagnostic function customized for device, and no direct connection to any other device. I will show you why the last point is a key point. So simplified scheme of working FDT DTM architecture is shown on this slide. As you can see, the frame application, it's usually a plant asset management system, carries all DTM components in its COM container. When the device DTM, the DTM component that works with field devices, wants to send some data, it will ask the COM DTM, the component responsible for talking over industrial bus, to send some data to the modem or gateway, and then the data will pass the modem and goes directly to the transmitters, and vice versa. Here is the screenshot of field care, a typical FDT container or PAS system. In terms of FDT DTM, it's also called FDT frame application. You can see the hierarchy of ICS network on the left of the screenshot. It's bad quality, but there are some transmitters, gateways, and even PLCs. On the right side, you can see the DTM component itself. It's ActiveX GUI front end with configuration for some temperature transmitter from Andresen Hauser. And on this slide, you could see the internal architecture of the DTM standard. It's a bit complex, but I want you to note two important things. First, XML is used as an internal data exchange format between frame application and components, and between components itself. And second, the data is encapsulated while traveling through the DTM architecture that is created inside of DT frame container. That is how it happens. So imagine an ICS infrastructure that is shown on the right. The HART transmitter resists on the current loop line. It is connected to some gateway that is connected via field bus, for example, Profibus, to the gateway, and the gateway connects the field bus to the Ethernet, to the plant asset management on the PC, on the server. When the DTM component of the transmitter want to send some data, it will go and pass all the DTM components from down to the up, as you can see on the left side of the picture, and the data will be packed, encapsulated, and when it reaches the Ethernet level, it will go injected into Ethernet and sent over ICS network. Then the data will be decapsulated on the devices, on the gateways, and at last it will be injected in the current loop line. We've talked about the great features of FDT DTM for 10 slides now, and it might be really good technology, but in reality DTM components are based on such technologies and use such features as shown. OLE 32, ActiveX, Visual Basic 6, yes, back to 19. .NET, COM, back to 19 again. XML, STA, the single-thread appliance, single-threaded, and remote process control, of course, Windows remote process control. So I think when FDT DTM is planned, it should look like a great car on the left picture, but in reality it became something like on the right. Strange thing. Okay, now Gleb will continue with our research scope.
Yeah, a couple of words about our research scope. So there are tons of FDT components and thousands of devices. So we somehow needed to adjust our research scope. In all, we wanted to answer some questions. So why is FDT DTM architecture is weak? What kind of vulnerabilities may cause compromise of ICS infrastructure? And what about FDT2 security? How about it? To answer these questions, we needed to take all the FDT components and check out which vulnerabilities they have and how much is. So finally we decided to bound our research scope to MDT Components that works with HART protocol, and we took about 100 of them. And
there are 3,000 licensed DTM components and about 1,000 for the HART. We took about 10% of it.
Yeah, and we worked with them. So why we selected HART components? There are some reasons for it. We're already done some research with HART protocol. We're familiar with it. And in past, we have developed some hardware tools to operate with and attack HART devices. And of course, HART protocol is a thing that's used in some critical infrastructures like power plants, chemical factories, oil, gas industry, and other dangerous things. It's interesting for us. HART, what is HART? HART stands for Addressable Remote Transducer Protocol, highway addressable. It was developed by Rosemont in mid-1980s and now supported by HART Communication Foundation. HART is an industrial protocol primarily intended for hazardous environments such as chemical factories, power plants, and, as I said, HART uses current loop communication link, and current loop lengths can reach up to 3 kilometers. And HART transmitters are often placed out of the plant building, for example, for controlling the environment's presence of toxic elements in the air and other parameters. This could cause some physical security problems. HART uses half-duplex master-slave scheme, communication scheme. It works over 2200 Hz frequency and has 1200 baud speed. Maximum HART packet length is bounded to 255 bytes on paper by standard, but in practice it can reach up to 8 kilobytes, and we checked it. In practice it works. In this picture you can see how HART frequency shift keying works. As I said, HART uses master-slave communication scheme. It means that master is a control component, my system, is asking device and device then answers. It uses frequency shift keying, and true bits is modulated with 1200 Hz frequency, and false bits modulated with 2200 bits. Hertz. To the attackers models. The first attack models we used in our research is when attacker somehow using a special crafted device managed to connect to the HART link. Device like this was developed by us and presented before, a bit later about these cool devices. Upon connecting to the current loop, attacker can passively sniff any data that's circulating on bus and even inject some data or impersonate node devices and send some arbitrary data to the control system, or impersonate with the control system and send some arbitrary data vice versa to the devices. Interconnection with the HART link is it looks like very pleasurable scenario. We can thank to long-range distance of HART links and sensor or actuators often located in uncontrolled, insecure areas. Such devices may be installed in kilometers away from main buildings with control systems with some control, and these devices are absolutely unprotected in the face of third-party connections.
Basically, it put it on the oil or gas or water pipeline far from away the control building. to control the pressure, maybe temperature, maybe corrosion or other parameters.
Right, like on this slide. Here's a photo from marketing booklet from some vendor. We also researched and looked closely to the DTM component for this device. As you can see, this HART transmitter, some device, it's connected to the current loop, and it's mounted directly to the pipeline somewhere in desert. I bet there is no one in kilometers away, and it's this transmitter alone with evil monsters in the deserts. No one helped him. Another slide. Here's the wired HART device connected to the current loop, and also we can see a wireless HART transmitter connects to the wired device with a control system. When wireless HART is have some security systems like encryption at least, and but wired devices are still vulnerable to third-party connection directly to the wires, and here we go. In our research, we used some hardware tools to working with and attacking HART devices and HART lines. These devices are on the left side of the slide. This is a HART shield. It is a HART modem extension board for popular Arduino board. And at the right you can see it's called ICS Cursor. It's a multi-purpose device for auditing low-level industrial protocols like HART, Modbus, or Profibus. This device can be controlled directly via USB cable from computer, or, for example, Wi-Fi or Bluetooth or any wireless interface that we can connect it with the XB interface.
Okay, now my time. When I'm planning that talk, I think about not showing or showing this demo, but I think I should show the quick demo from that we have demonstrated at Black Hat USA. Maybe someone have been on our talk at Black Hat USA. Any hands? No one. Okay, that I'm right. Okay, this demo demonstrates how easily you could inject in the current loop line what you want. This is an attack on FDT infrastructure, of course, but it's attack on the FDT frame. The rest of the talk will be about attacking DTM components, not the FDT frame itself. But this is attack on the FDT frame. Okay, here is the quick about demo infrastructure. We have field care. It's a plant asset management system, FDT container. We have a SAP system. The field care is connected to the SAP system and periodically sends some data about ICS to the ERP. And it's divided by firewall that allows only HTTP traffic. Also, we have a HART modem that is connected to field care and the industrial transmitter on the current loop. Here we use the vulnerability in SAP. It was found by Dmitry Chestuhin 2 years ago, but this is only as a demonstration how we can extend our attack through the ICS network from the lowest level to the highest level. Okay, now I think it's time for some video demo. Could you bring it, I think? Oops, that's wrong. Так. Okay, let's start. So here is my lab, and here is our lab. And as you can see, this is a transmitter. This is the oscilloscope, and you could see that the HART signal is going through the oscilloscope, and you can see the pass system. Here it is, and it gets some data from the transmitter. The transmitter isn't connected to the real sensor, so we can just monitor the current loop current. and the transmitter is without case. Usually transmitters are packed in the heavy steel cases. In our lab, my table will be broken with this shell. So we've removed the shell from it, and this is the field care system. It gets some data from the transmitter, and on the right you have seen the DTM component, and this is the SAP system. As you can see, you could reach it by HTTP. Now I have written some Metasploit model. You could find it on my GitHub. I will give you a link at the talk. And here is the ICS Cursor board. It's connected to the laptop with USB, and I just need to connect two wires to the current loop. I can do it directly by connecting via resistor, or by using silver needles. Just insert needle into the wire, copper wire. That's enough. The HART is a very reliable protocol. It will work. It is designed for this. Now I'm connecting. This line could be up to 2 kilometers long. ICS Cursor is a very powerful device, and wrong USB device. I will set the correct port of the ICS Cursor, and now run, and the shell will appear in a minute. As you can see, at first we are jamming the line, and the modem, HART modem, going crazy, HART gateway or HART modem, and as you can see that the error is in the field care interface. And what's the typical reaction of the field engineer if he sees such faults? He will restart, reconnect, rescan the current loop for faults. So he did it. He did it now. The rescanning started. And as you can see, we've got the shell on the SAP server as it planned by the developers of MDT DTM, I think. Okay. Could you take it for some time? Now, I think I could return to my presentation. Just a second. And give you some explanation. Okay. So what was happened? We have changed the long tag variable on the HART transmitter. It's internal variable that is get by the plant asset management. This variable, when it's going to through the plant asset management and through the DTM, it going through the XML document. Remember, I've talked about XML. And of course, if we put a single quote to it, we have XML injection. Then we load the external XSS scheme from the evil web server that contains server-side request forgery code. If you want the more details, you could look at the Black Hat USA 14 white paper. A good explanation in it. And finally, we have SSRF to the ERP, and the remote command execution query will send to the ERP. So, as you can see, it's very easily to inject into the current loop line. It's by HART design. Gleb?
Yep.
Чуть быстрее.
Oh, so let's back to the attack models. In the second attack model, the attackers to connect to the industrial links, which are tunneling the HART data. For example, it may be Modbus or Profibus. And third attackers model is a classic intrusion in the well-known IP networks, which also may transport industrial protocols like HART, or interception of long-range radio connection links to the control station, just like on this slide. It's example directly from an Emerson promo video. Here we can see a HART link that encapsulating into the long-range radio channel to control system. Again, somewhere in wild desert. Industrial devices like deserts, I think. So, at all, we got 114 DTM components from 24 vendors and for 752 devices.
It's a big scope.
Here are some vendors of DTM components that were researched, and we have found some bugs in some components made by these vendors too. All the DTM components can be that we are researched can be divided in two big groups: developed by vendor itself and developed by outsourced company. Almost half of all components were outsourced to only two developers. It's CodeWrites and MMDM. You could see that the distribution on the screen, 35 components were developed by MMDM and 15 by CodeWrites. These outsourced agents have their own DTM frameworks to, you don't believe, they may generate it automatically. It's very good for us because all the automatically generated components, of course, have the same vulnerabilities. So, how we try to fuzz it and how we fuzz it, that's all. A lot of components, they're all very different technologies, different frameworks, different programming languages, different internal communication models and methods. And we used three slightly different fuzzing methods. Is a communication component emulation, software emulation of physical device, and true hardware emulation of physical device with all real other components. Here is a software and hardware toolkit that we used in our research. First is HART parser, is our written dissector library for a HART protocol. Second is HART emulator, is a Ruby written very flexible HART packet generator that uses first HART parser. And DTM fuzzer is our custom DTM communication DTM component that we used for proxifying data. And fuzzframe. Fuzzframe is an emulator, fully functional emulator for frame application, for pass frame application. We can load into it all the other DTM components, and they worked inside this component, and it can log any data, all internal processes, all internal interconnections of the components. They are all logged by DTM Spy. It's a part of fuzzframe. And as I said before, we used a couple of hardware tools, as ICS Cursor and HART Shield Arduino. The first way we used was a software-defined device simulation through our communication DTM component. We loaded the at left up, we can see that we loaded the target device DTM that we researched at the moment in the real frame application. It's we use field care and configures it to work with our HART fuzzer DTM communication component. When the device DTM requests some data from the virtual device, device DTM don't know that it's not real device. It sends the request. requests transport through the UDP protocol from our communication DTM component to our HART packet generator and parser. It parses the request with help of HART parser and form the answer and somehow mutates it with our fuzzing rules and with some redemption magic.
Finally, with some redemption magic, it is mutated.
Yep. The second fuzzing model is similar to previous one, but here we used a real-world communication DTM, which communicated with our emulated device through the virtual serial interface. Fuzzing parts of this method is the same as the previous. And the thread and the most realistic model, we used it to check bugs that we found, is a fully hardware device simulation with ICS Cursor board that controlled with the same HART library with fuzzing logic as before. Our special device connected to field care with a current loop and a real HART modem. And in field care, the pass application, we loaded the real communication DTM component and finally target device DTM. And this way we're trying to trigger real vulnerabilities.
Okay, and now it's time to talk about results. I hope you don't get bored. The final result is shown on the picture. So, as you could see, we have 29 components with vulnerabilities, and the rest is not vulnerable. Maybe not vulnerable because we didn't spend very much time on fuzzing, and fuzzing still continue. And since the fuzzing stopped, we have found at least 3 bugs more, but they are not here. You can see that is about 25%. You could grade it as a good or bad result, but look at the diagram on the right. We have found bugs in the most of devices. So unfortunately or fortunately, the vulnerabilities have been found in the components that covers many devices, about 67%, about 500 devices. That's bad or good? Good for us, bad for ICS, as I think. Here is the distribution of vulnerabilities by type. We have found several confirmed remote code execution and have proof of concept exploits for them. I will show a video of one exploit at the end of the talk. Several race condition, of course, and denial of service that could crash DTM, could crash container, could crash the industrial bus device drivers, and could totally crash the Windows XP system and Windows Vista system. We tested on this system because it's the environment, usual environment for such systems. That's it. Also, in 7 cases, it could be possible remote code execution, or at least memory corruption, or denial of service. We didn't have developed the proof of concept exploits for them. It's in progress. Also, we have 2 XML injections, like I've showed you in the video demo, but not in the FDT container, but in the DTM component. 2 XML injections, and several other vulnerabilities such as freezes, long-time freezes when the system freezes, some strange abort functions, strange, and of course we found one cross-site scripting, XSS. That's nice. I will show you it. Here are some of messages that we've got during our fuzzing, from denial of service to the memory corruptions, written to protected memory, unhandled exceptions, overflows, other things. That's funny. Nah, really, I really want to show you all the crap that we have found, but I can't do it right now. Sorry guys, we are a bit whiteheads, so responsible disclosure, sorry for that. We'll show only some funny and strange things and the vulnerability demo with hidden vendor and device names. That's all we can do. Responsible disclosure, sorry. But we can show you the distribution of found vulnerabilities by vendor in two views, by DTMs and by the devices. As you could see, for example, Anderson Hauser have vulnerabilities only in several components, but the devices that are affected by these vulnerabilities are really large count, about half of all devices. That's how it works. And the same stats, but for all sources, as you can see, using or not using outsource will not affect the resulting quality of DTM components. About 50%, 50-50. So time for some fun, and we'll show you some strange vulnerabilities and funny things. As I said, you won't believe it, we found an XSS cross-site scripting vulnerability. Of course, it's not usable due to the payload size. It's a really small payload. For JavaScript, it's really small. And there are content security policies, so they will not work in reality, but it's really funny. The configuration datasheet in the SV2 AP HART DTM from GE Oil and Gas is formatted using HTML. You could see the GA logo, cool logo on the right. And the device tag and long tag are going there unfiltered, as always. So you could insert about 40 bytes of JavaScript code there, and the funny alert will appear. Also, I don't like Anderson Hauser company. They always ignore my vulnerability reports. They don't answer for years. So now I disclose it. Partly disclose, of course. I always knew that they're ignoring standards too. So as you may remember, the maximum length of HART message is about 255 bytes. But the Anderson House developers write software that crashes even on the legal, according to specification packets. We've sent just 217 bytes, and what we see, you can see, overflow. They just don't read the standards. It's a denial of service because the DTM component is written in the Visual Basic, but how could they develop in such a way? We just sent a legal packet, got crashed. Also, some of developers of DTM components are too lazy or too coward to even fill the executable strings, to do company name, to do file description, to do product name. Maybe they fear that the real users of their components will catch them and bite after such software quality. And here is the really nice thing. As you could know, there is a secure version of memcpy-s. Here you could see the really secure usage of memcpy-s. As you could see, the second parameter and fourth parameter are the same. SRC size multiplied by 2 is equal to count. So they're using memcpy-s as a memcpy without security mechanisms. And it, of course, leads to the denial of service or even worse. That's the secure usage of memcpy from the MMDEM software game bash, and now I know who is working for this company and how they're writing such code. Okay, here is the IRC remote code execution demo video. We will run the calculator through the current loop. I hope I can do it. Okay, here it is. As you can see, we have filcare and the component inside. The vendor is hidden, of course, responsible disclosure. And you can see we're starting our fuzzer. And just read data from device. It will be really fast. Yes? And here it is, the calculator. As you can see, it runs through the filcare frame. Moreover, as you can see, we just now cancel the transaction, the timeout will pass, and the filcare will stay alive. So we could remotely execute code in the context of the filcare, and the field engineer won't notice anything. The filcare just contains the normal work, and the calculator is running. So, just a second, I will continue. Another statistic slide. As you can see, we've already seen the code quality of some DTMs. It isn't very good. Moreover, most DTMs were compiled without essential security mechanisms. That's why we could say that so much RCE could work. As you can see, only 7 number of components have stack cookies, data exchange protection, and under space allowed randomization enabled. The most of the components have it disabled at all. That's really good for us, really bad for vendors. We need to do something to attract the vendors' attention to this. Now, as you can see, FDT version 1 isn't good from security point of view, but recently FDT group introduced a new specification, FDT version 2. Let's talk a bit about it. The key differences of version 2 versus version 1 that could interest us from security sides are .NET based. It's now only .NET, no more COM, OLE, Visual Basic hell, and the absence of XML. The interaction between FDT objects is based on .NET data types rather than XML. But these changes really looks very good, but there are several pitfalls. First, it still has very low spread over the industry. We didn't see any FDT version 2 component in the wild. Even we didn't see in the official FDT group catalog on their site, fdtgroup.org, there are no such components. So I think they didn't exist, only standard exists. Also, FDT version 2 has a backward compatibility, an ability to deserialize or serialize .NET objects into XML for working with the previous components. So infrastructure could be built of FDT version 2 and FDT version 1 components. So nothing changed in this site. If you have at least one FDT1 component in the infrastructure, nothing will change. Also, managing code, it's a great idea, but it will not be a complete solution if unmanaged code is still used. For example, we've seen some DTM components with really, really secure front end on .NET or Visual Basic, but inside it calls an unmanaged C++ code with such memcpy-s or other funny things. Unfortunately, as I said, we couldn't find any real device supported by FDT version 2 to test it. If you have one, we can borrow it from you for some time and write a next presentation. The other thing that I think isn't very good about FDT version 2, it's the relation of FDT group to the security. We found a bug in one specification about a year ago. They published the security paper about it only several weeks ago. A year have passed. Moreover, they didn't mention us as authors in its security bulletin and named us as a group of Russian hackers. Not a digital security company, not an security researchers, but a group of Russian hackers. Moreover, they, in its security bulletin, they just filtered the double quote. They have a year to fix the double quote filtering to make a security bulletin. They have a single quote. They have an ampersand in XML. I think it will take several years. Also, they have a bunch of RCEs. I want to know what they will say. So, time for conclusions. We are planning to actively work with vendors, directly with vendors, through the ICS CERT or through the CERT, I hope, to solve all discovered problems. We didn't disclose it. The full report on found vulnerabilities will appear, we hope, of course, in spring, summer next year. We could not publish more information at this point and could not release some tools, because of irresponsible disclosure, I've said. Also, we plan to publish the sources. The same time next year, during our research, we've fuzzed about 114 components, found 29 at this day 32 vulnerabilities, and the quality of most components is lower than medium. If you have one of 500 different hard devices with vulnerable DTM components in your industrial facility, you could be at risk. However, these attacks are possible only because of not only because of DTM weaknesses, but also due to fragile ICS infrastructure. The approach to the whole ICS multi-layer network should be changed, as I think otherwise we will face the risk of such vulnerabilities over and over again. FDT version 2 could compensate, if used with care, of course, some problems, but unfortunately it isn't actively used now. So what we can do now is just awaiting vendors' responses and hoping for the best. We always hope for the best in the ICS security. Here are some links. The first repository didn't exist. It will be created and filled upon the vendors' responses. I could not put the real fuzzing code there because you can fuzz and disclose such bugs, so sorry. I hope in spring it will be filled. The ICS Cursor, HRT Shield and HART parser are open. You can download, you can solder, you can build the devices, you can experiment with them. The research was a bit hard. Usual thanks again series. We want to thank Svetlana Cherkasova and Georgy Nosenko from our lab for some binary magic and great help in reverse engineering and creating proof of concept exploits. Andrea Bakumov, our junior security analyst, for help in finding XML injections. My friend Fer Savelyev for some fuzzing ideas, and the great artwork by Alexander Popov, great background picture for the presentation. We are done. Sorry for our bad English and awful Russian accent. Sorry for that. Any questions?
So what would be your recommendation to the users of the technology who are typically not able to fix any of these problems, but they have obviously, as you described in your introduction, these products? So what is your recommendation to them?
At last, in that security bulletin, there was some right thoughts, as I think. You need to deploy some firewalls, of course, on the between middle and high level of the plant to prevent loading the external XML schemes, XXEs, other things. And as for the lower level, physical security, and maybe you could use some special firewalls between the layers from Tenable or some other things, from some Splunk devices and other things that could detect the exact attack signature. So you could just implement an attack signature. For example, in the IP tables, when, for example, you have a current loop connected to the field bus and field bus connected to the Ethernet, you could put between plant asset management and Ethernet field bus gateway your server with IP tables, for example. It's a cheap solution. It's a free solution. And directly write the signatures with deep packet inspection and deny such packets, just based on the exact vulnerabilities. That's if you cannot build the really secure from physical secure environment and cannot defend from injections on the Ethernet, on the wireless networks, and on the field buses and current loops, that's the only solution I could tell you. Another question? Okay, thank you very much for your attention.